All right, so we've made it to the end of chapter 9 here on our unit on significance tests. We have one more kind of modification of mu problems to talk about called a paired t-test, which we'll get into. We're also going to talk about a few just kind of misconceptions or just things to be aware of in the back of your mind when you're looking at studies that use significance testing, which is pretty much every study ever. So just good need to know stuff at the end of this lesson too. Before we get into that, though, we are going to look at an example right here. So what we have going on is two sets of data in this problem. There were two girls for their AP Stats project end of the year where they do their nice little research setup. They wanted to see if the express lane at a grocery store was actually faster than the regular lane. So what they did is they both randomly selected times when they were going to go to the store. They went to the store, got the same item, and then they both entered their checkout lanes at the same time. It was randomly assigned who went to each lane. But one person went into the regular lane, one person went into the express lane, and their matching times are shown side by side right here. So these two times are when one girl went in the express lane, one girl went in the regular lane at the same time. So those two numbers are linked together. The same thing with these next two numbers and these next two numbers, etc. So instead of organizing or analyzing, the two separate data sets, when you have two data sets that are really linked together, because when they went at these different times, maybe the store was pretty busy right here, where at this number it wasn't as busy and stuff like that. Each pair of numbers is sort of on the same playing field. It happened at the same time of day, they bought the same item, etc., etc. So what we do frequently when we have data like this that's linked together or paired is instead of analyzing these actual numbers right here, the raw numbers, what we're going to do instead is we are going to analyze the difference between these two numbers. Anytime you talk about difference, you should specify the direction you're subtracting. I'm just going to go express minus regular, although it doesn't super matter as long as you declare what you're doing. So rather than looking at the one girl's number over here and the one girl's number over here, we don't care about those. We just want to do math on our difference. So my first difference, 337 minus 342 right here, would be a negative 5. And then we're just going to go from there and keep on subtracting these combos. I'll pause and come back with those solutions. All right, so in orange, you're going to see all of the differences between each pair of numbers right there. When you conduct a paired test, the original data doesn't matter to you anymore. You're only going to look at the difference column right there, and those are the numbers you're going to analyze. So if you need to graph your data, if you need to do some sort of significance test on them, we're going to use our orange numbers to do these. The original data is good. We don't need it anymore. Okay? So what we care about in this problem, let's think first about what these numbers mean. Anytime you're doing a difference problem, you should ask yourself, well, what would a positive number mean? What would a negative number mean? Like my first number right here is negative. If you go express minus regular and you get a negative answer, well, that means regular was a bigger number, or in other words, express is faster. So any numbers you see right here that are negative are times when express was faster. A positive number, on the other hand, would mean the express actually took longer or regular was faster. So always look at that when you're doing difference problems. It's a frequent thing they'll ask about in the AP test as well. What we care about in this problem, we want to look at mu. And I'm going to put a subscript of D on my mu for this problem here. Common thing that you'll do when you're taking the mean difference. So we're looking at all of these differences here. And we're actually going to analyze the average of the differences that we just produced. So mu sub D is going to represent the mean difference in checkout time. And that was express minus regular. And then we're going to conduct a significance test because these girls' whole goal was to see if on average the express actually is faster. So think for yourself here. Before I put down what my null hypothesis is going to say, The null hypothesis would say, hey, there's nothing going on here, status quo, there's no difference between regular and express. What would mu equal in that situation if there was no difference between the groups? So what you should have said for that is that the mean should equal 0. We're going to go into the problem assuming there is no difference between regular and express lanes, which would mean that their difference on average is 0. We are seeking out evidence in this problem for our alternative. We think that actually the express should be faster. So if there's convincing evidence that the express lane is faster, what would that mean? Is that a positive answer or is that a negative answer for the mean difference? We did already talk about that, but express is faster if it's a smaller number, which would mean that you get a negative answer. So we are seeking out evidence that actually the average of all these orange numbers right here is less than 0. That would mean that on average, the express lane is faster. We're going to go ahead from here and check conditions, and then we're going to go ahead and you can do the calculator way. I'm not going to make us calculate TCDF stuff. Go to t-test. This time, you're going to type in your orange data. So pause me. I'm going to come back with solutions on here, but from here on out, after you get the differences, we're just doing regular, good old t-test stuff like you guys already know how to do. All right, so coming back with the actual answer here, work's kind of going all over the place there, but a couple of things I wanted to comment on. First of all, when you type in your data and everything like that, remember you're using the orange difference numbers, and that's all fine. When I went stat for this problem and I did my t-tests, I chose the data tab because I didn't know the statistics this time, just the raw data. I left it as 0, etc., did a less than alternative, and when I calculated, I got the following setup for my p-value. So my p-value was about 0.034. Don't forget to include your test statistic as well, which I have written down over there. And there's two things actually that as my answer is currently written, I do not have. So I have my setup right here in my condition check. I forgot again to declare an alpha. I've done that a couple times, but you always need to establish your alpha before you collect your data. So when you set up your alpha, again, 0.05 is the most common, but that is up to you. We're going to talk at the end of this video about sort of dishonest things you could do in a situation like this with data where you need to make sure you're doing the right thing when you do your research. Let's say I had said, I want my alpha to be 0.01. I just set that up ahead of time, 0.01. And then it came back and my p-value was like 0.03. Well, failing to reject isn't super exciting. I don't make research journals. I'm not going to make some article by saying, oh, I failed to reject my null hypothesis. My evidence wasn't statistically significant because statistically significant means you had a low enough p-value. So nobody gets published doing stuff like that. So let's say I said, oh, I want 0.01, but then I find out, my p-value was 0.03. Well, I'm going to change that to 0.05 now so I can actually be statistically significant. That's not an okay thing to do. Once you set alpha, and you need to set it ahead of time, you have to commit to it. I also forgot when I wrote my little statistic, my do step over here, I neglected the degrees of freedom, which kids forget that all the time because the calculator doesn't explicitly give it to you. Whenever you do a mu problem, you need to make sure you report your degrees of freedom. Remember to do that, please. And then one more thing, when I wrote my conclusion, we've got our little script down. You guys are used to talking about how to write a conclusion. Instead of just saying there is convincing evidence for HA, I could say there is convincing evidence that the mean difference in checkout time is less than 0. I put a little spin on it and I talked about there is convincing evidence that the express lane is faster. If I would have stopped at faster and not said on average, you will lose credits. Never lose sight when you do these problems that we're testing the mean. We're not saying express lane is always faster, just that it's faster on average. So bottom line, this is just another problem right here running a significance test on mu. The only difference is that we analyze the difference data sets and then we go from there. So with our big problem out of the way for the video, I want to talk about a few misconceptions / things to keep in mind when you're analyzing significance tests in general. So this is just an extra work slide right here. But first thing I want to do is I want to talk about just being careful with p-values in general. I'm going to go back to the don't break the ice problem because that is still fresh in my mind right here. Actually, you know what? I'm going to do the sub problem. We looked at average sub length a little bit ago, and our null and our alternative hypotheses looked like this. Anytime you get a p-value for a problem, your p-value should always be a decimal. It is always a decimal because it represents a probability. Sometimes when your p-value is super low, kids will see, like when your calculator does scientific notation like this, they'll look at this and be like, oh man, my p-value is 4.32. Really bad thing. Don't ever get fooled by that. Okay, so that just know that if you get a number like this, it's probably in scientific notation. Another thing that really shouldn't happen when you conduct a p-value, especially on a one-sided test, you really shouldn't get a p-value above a 0.5. Okay? In a two-sided test, it's harder to tell, but in a one-sided test, that really shouldn't happen. Because let's talk about what that means. If I'm doing a problem where I'm looking at the average sublength, I think the average is actually 6, and I'm looking for evidence that the average is actually less than 6. Let's say I take a little sample of subs, I find their average, and my x bar in the problem was like a 6.2. The average of my sample was 6.2. Well, think about what that would mean about finding your area. 6.2 is like somewhere over here on this side of the picture, but I'm doing a less than problem. So anytime you do a one-sided test, if your area is over a 0.5, you should honestly feel like a little bit silly when you did that. Think about the courtroom analogy that we talked about earlier. There has to be some evidence supporting your alternative hypothesis. Otherwise, you're wasting your time by doing statistics. If I think, man, I think the average sub is under 6 inches long, and then I take a sample and I get 6.2, throwing that into a t-test is a complete waste of my time. I'm going to get a p-value that's over a 0.5 because this doesn't even support what I'm trying to do in the first place. So if you ever get your sample evidence that just straight up contradicts your HA, don't do statistics. Just go home. Problem's over. Okay? So be mindful of that in general. We usually see pretty small p-values because if you were going to get a big p-value, you should probably notice and shut it down before you even do fancy stats in the first place. I've got some other observations and comments here that our book talks about. Just other things to keep in mind when you're running significance tests of your own or when you're reading research that someone else has done. So there's a lot of stuff going on right here in terms of just looking at things overall with sample size. Remember, first of all, that if your significance level is lower, that means like going from alpha equals 0.05 to 0.01. If you pick a smaller alpha, that means you need stronger evidence before you reject the null hypothesis. If you lower it to a 0.01, that means fewer p-values are going to beat that cutoff right there. So you're not going to reject as much. So when you lower your significance, your alpha level, you're saying the evidence needs to be stronger before I reject. So if you're in some life or death situation where rejecting is a big deal, you're going to want to have a small alpha. Most medical trials and stuff like that are going to have lower significance levels because the risk of being wrong is oftentimes very serious. On the other hand, we have power, and the idea of power, remember, it's that being able to detect a discrepancy. You want to notice a difference when it actually exists so you can avoid a type 2 error. So remember again, as far as power goes, power is all about avoiding a type 2 error. And then the last piece right here talks about no matter what your significance level or power that you want to get is, being able to detect a difference is easier when the difference between HO and what really happens is larger. So in my potato truck example, if you guys remember from a few videos back, if I'm supposed to have 8% bad potatoes, finding 9% and noticing that, maybe I'm going to miss it. It's kind of close. Finding 90% bad potatoes, opening that truck and they're just rotting everywhere, I'm going to notice right away. So having a bigger difference there is going to make it easier to be able to notice that difference in the first place. This concept right here, I didn't talk about this in the power video, but this concept has a fancy statistics name called the effect size. So being able to detect a difference is easier when they're actually farther apart. Okay? So that's the basic idea right there going on. Couple other things that I want to talk to you guys about in this video here. This next thing is kind of hard to understand. So I'm going to break down what this is saying. And I see my text box is a little too small there. That's unfortunate. This part, if it's confusing to you guys, it's okay. It's a little more of an above and beyond thing. But when you're looking at a problem, you have to beware about getting too much data, too many people in your study. Now, you may be saying, like, why would that ever be a bad thing? Why would having too much data ever hurt? I'm going to use the sub-example that I just did a little bit ago. If we know that the mean sublength is equal to 6 as our null, and our alternative is that it's actually less than 6 or not equal to 6 or whatever you're going to do. I'm going to use not equals because it's a little easier to understand here. In reality, if we're being honest with ourselves, what are the odds that the average of every single sub is exactly down to like the millimeter of a millimeter, just the tiniest little nanometer, whatever you want to call it? What are the odds that the average is exactly 6, like we're assuming it is? Well, we've talked before, it's probably not exactly 6. Like, that's almost impossible to hit it dead on. So we start with an assumption in this problem that honestly probably isn't true. It's probably not exactly 6, but it's probably pretty close. So here's the thing. If my mean really isn't 6 and it's really like 6.000001, something like that, technically HA is right and HO is not. HO is almost always not correct because how likely is that it actually equals that exact value? So when you do problems and you get too much data, you may end up getting where you reject HO, you find convincing evidence of something, but just because you find convincing evidence doesn't automatically mean, oh my gosh, I'm being lied to. This is such a huge difference. This is like a big deal. You could be picking up on a really, really minute, tiny difference that isn't really consequential. Okay? So basically what this is saying is no matter how like tiny that difference is, if you take a large enough sample, you might pick up on some sort of difference right there. So just because there is a difference doesn't automatically mean that it's going to be meaningful. If that last 2 minutes was like iffy, confusing, I get a lot of weird stares when I talk about that in class. It's okay. That's more of a minor kind of above and beyond thing, but just something to be aware of if it does make sense to you. This other thing that's written down right here, when you look at these problems, I have a comic that actually illustrates this idea better than just reading it to you guys. So you need to be careful in general with what happens when you do multiple analysis or when you analyze lots of different things in succession. So the idea with this comic, we got a sweet XKCD comic right here. They are testing jelly beans and they're looking at whether jelly beans actually cause acne. So that is what is under study. So they do their little test. They run a significance test on their data and they find that there is no link between jelly beans and acne. The p-value in their problem, as you guys can see, was above 0.05. So, okay, fine. Jelly beans don't cause acne. But wait, it's actually a certain color of jelly beans, apparently, that cause acne, they think. So then they go and they test all these different colored jelly beans. They looked at purple jelly beans, p-value's too high. They looked at brown, the p-value's too high. Pink, blue, teal, salmon, etc. All of these times, unsurprisingly, there is nothing statistically significant going on. These different colored jelly beans don't cause acne. But then, in that one brief, amazing trial right here in this panel of the comic, they did find a low enough p-value for green jelly beans and acne. So in that one trial, wow, the p-value was low enough. Oh my gosh, green jelly beans must be what cause acne with 95% confidence they can report that. Okay? So the idea with this comic is you have to remember that when you do a significance test, if you have an alpha of 0.05, that still means in 5% of trials, 5% of samples that you get, you could achieve those results, even if there's not really a statistically significant difference going on. They tested, if you guys count here, there are 20 different colors that they tested. 1 out of 20 is 5%. So if you test enough things in succession, sooner or later, you're going to have one that defies the odds. And it's like, oh my gosh, something's going on here. So what you need to realize is that if you test a bunch of things, just because you get significant results on something doesn't mean anything. That's why so many trials, when they're retested, kind of fall apart. You'll hear about like this amazing new wonder drug, and then it will fall apart after repeated trials. When you get those significant results, it becomes important that you test again. If we tested green jelly beans again, and a second time they were statistically significant, then there would be something going on. Okay, so just a lot of kind of things to think about right here with regards to just using significance testing wisely. As long as you're following good practice here and you're kind of at least aware of these things that are going on, when you read a study, you should be able to analyze it with deeper understanding than you guys could previously.